Hello there and welcome to this video on program construction. There'll be two videos in total for this chapter and it's for AS and A2 students. I'm going to point out the sections that are AS and A2, but it's all worth learning because you'll all be studying it in the second year. So we're going to jump straight in. If you look at these two images here, you'll notice that the hardware is what we call the lowest level. At the top of this little block structure, we have our high-level languages right at the top. So high level means closest to English. As we go down and we compile our code, we're trying to get down to machine code, and we do that through a series of steps, and that's called the compilation process. Now, to compile or interpret or assemble your code, there's a number of different steps that have to be carried out. But first we need to look at what are compilers and interpreters and assemblers. Well, they are all forms or types of translators because they convert one language into another. So high-level language into machine code, which is binary. And once we have our program in a binary format, then we can interact directly with the hardware. So let's have a look at compilers. Compilers, they convert source code written in a high-level language such as VB.NET, Java, C, C#, C++, etc. into machine code. But at some point, if you need a program to program a program, how do you program a program to program a program to program programs? Well, the answer is machine code. And yes, people used to write in machine code, and one, it's very difficult to do. Two, it's very prone to mistakes. And if you change just one zero to a 1, then it's likely your program won't work as expected. And that's where the invention of assembly language came in, and then now our modern day equivalent is a compiler writing in a high level language. So compilers, they produce a standalone executable file. There is no need for further compilation because you have a package of machine code. A program is then compiled once, but it can be ran many times, and that is very efficient. It also protects the intellectual property of the developer and the source code. And believe it or not, this is very, very important. We know about the classic battle between Microsoft and Apple, Bill Gates and Steve Jobs. Now, their CPU instruction sets are different. So when you compile for Mac OS X, for example, and you compile for Windows, they are not compatible. Windows runs on exe files and Apple computers, they run DMG files. And they've done that on purpose to simply capture more of the market. But just imagine if you could compile for any architecture-specific platform that you wanted. That would be the goal, wouldn't it? If you have a mobile app, you're going to capture more of the market if your app can be run on different platforms. And that's where interpreters come in. An interpreter handles the job of translating code very differently than a compiler. Each line of code is translated into machine code line by line, and this is done every time you want to interpret a piece of software. The interpreter takes the first line of the source code and translates it, executes it before moving on to the next. Any machine code produced while the interpreter is running is not saved. The interpreter must interpret the code every time the user wishes to run it. So why do we actually use interpreters? Well, in order to be able to run an interpreted language, you need to have an interpreter piece of software installed on your system. The interpreted languages can be run on any system as long as the interpreter software is installed. And that's a major benefit because source code has to be written only once and then it can be run on any computer with an interpreter. And it's also better for debugging because you can easily inspect the contents of variables as the program is running, and you can test code much more efficiently, as well as being able to test single lines of code. And obviously, the major benefit is the multiple platforms that you can run your software on. Now, obviously, there are some disadvantages as well. You must have an interpreter running on the computer in order for it to be able to run your program. As source code must be interpreted each time, interpreted programs can sometimes run slowly. And you may have to rely on the interpreter for machine level optimizations for different architecture rather than programming them yourself because you don't know what specification you are programming for. And the final problem is developers can view your source code. So your intellectual property, it's not yours. A little bit of a recap then. Compilers, source code is hidden. Interpreters, it's visible for all to see. Multiple platforms, compiler-specific architectures, interpreters, as long as the software is installed, run it anywhere you like. Distribution-wise, well, you can distribute over a memory stick, CD, internet with a compiler, but an interpreter, again, software needs to be installed. Library files all need to be installed, so it's a little bit more of a faff. Now we're going to look at assemblers. So the process of actually getting from assembly language to machine code is the process of assembling. Now, assembly code is a step above machine code, but it's still a very low language. But it allows the programmer to write code using something called mnemonics, and they represent a machine code instruction. So each assembly code instruction has what we call one-to-one mapping with machine code instructions. And that means we reduce the need for ambiguity. So it's unambiguous. You can only interpret it in one possible way. Now at this point, AS students, you can switch off for a second. A2 students, you need to know how this process works. So translating assembly to machine code, because we know it has a one-to-one mapping, we take a two-phased approach. In the first phase, the labels are converted into machine code addresses and stored in something called a symbol table. Symbol tables in assembly work different to those during the lexical analysis, which is covered in the next video. The second phase of assembly involves converting the mnemonics of their binary representations and combining them with the binary representations of the data. So for those people that have studied assembly language before, using the LDA commands, STA commands, etc., they are your mnemonics. So it's converting those and giving them a binary equivalent. And once we've assigned them all binary numbers, then what we can do is we can put them all together and process them on the CPU. So when we write in machine code, we know that it's very time consuming and we know it's prone to errors. And when converting assembly to machine code, use an assembler, which is a form of translator, as is compilers and our interpreters. Converting assembly code into machine code is known as assembling rather than compiling, and that's really all we need to know at this stage on assemblers. A2 students, again, this is just for you. Virtual machines, they use something called intermediate code. And virtual machines have been around a long time. But it allows you to represent another operating system inside the operating system that you're currently running. And virtual machines act as interpreters for generic machine code instructions known as intermediate code. Think of intermediate code as a semi-compiled package of code that's then interpreted using the virtual machine. And that means it can be run on different architectures or operating systems. The generic intermediate code cannot be ran by the CPU directly. It's basically an abstraction rather than a real instruction set. And we can't run this code unless we have the virtual machine installed, just like the rule for interpreters. Let's summarize that process. The source code goes in, or the programming code that you've done goes into the system, and you can go one of two ways. You can go down the translation route, including interpretation. So you can interpret your code providing you've got that software installed, and it will convert directly to machine code. Or you can go down the translation route involving the compiler, which we know produces an executable file. It'll produce object code for you and a library as well. Any libraries that you import need to be binded to your object code through the linking process. Once it's linked, then it's converted into machine code and you can run it on your specific architecture. Or you can create something called intermediate code that we just looked at, and then you can install your virtual machine, and that can be interpreted into any architecture set that you deem fit. And that's it for our first video on program construction. Join me in the second video where we'll be talking through the compilation process and the stages involved in that.